Welcome to today's Solvay Colloquium, which is, for obvious reasons, entirely online. So our speaker is Professor Geoff Penington from UC Berkeley. Geoff got his master in natural sciences from Cambridge University in 2015 and his PhD in physics from Stanford University in 2020. He became assistant professor at the University of California at Berkeley that same year. He's currently junior visiting professor at the Institute for Advanced Study in Princeton. He has made profound and very exciting contributions to resolving black hole paradoxes and understanding quantum information in gravity. His contributions have revolutionized the field. We are very pleased that he accepted to deliver a Solvay Colloquium on this subject. So Geoff, the floor is yours. Please go on.
Okay, wow. Thank you so much. Yeah, so this talk is called Black Holes, Information and Wormholes, which obviously has a lot of fancy exotic things in it. But I'm going to start with something a little more down to earth, namely an egg. And we're going to take this egg and we're going to drop it and it's going to hit the ground and do what eggs do and explode. Okay, great. But now what we're going to do is we're going to stop time. Oops. We're going to take every single particle that is exploding away from that egg. We're going to take its velocity and we're going to reverse it. We're going to point it back at the same speed in the opposite direction. And finally, we're going to start time again. So what's going to happen? Well, the answer that may be surprising or not surprising to you, depending on how much physics you know, is this. The egg will zoom back together and pop back up into the air. So the most fundamental level, the laws of physics, as we understand them, are reversible. The laws going forwards in time are the same as going backwards in time. You can take the sort of final state, reverse time. Technically, you need to do some things about turning particles into antiparticles and so on, but we won't worry about that. And time will just go backwards and everything will happen in reverse. So there's another sort of similar way in which we can think about essentially the same phenomenon, just that if the laws of physics are reversible, then information present at one time is always present at another time. It might become less accessible, but it will always be there. So what do I mean by this? Well, let's imagine that I have a book and I want to erase forever the contents of this book. Maybe it's my secret personal diary. Maybe I'm just a bit embarrassed about my reading choices. I don't know, but I want to take this book and I just want to prevent anyone ever knowing what was inside it. Well, how would I do that? In practice, I might do something like taking the book and shredding it. And, unless somebody really, really cares to know what book I was reading, that'll probably do the job. They're not going to find out. But with sufficient effort, they could take all those shredded pieces, match ones up to each other, put it back together, and eventually they'd be able to work out what the book was. They'd be able to recover the information that was initially present. So we haven't quite managed to destroy information there. Let's try something a bit more sophisticated. Let's take well, not really sophisticated, but never mind. Let's take the book and let's just burn that book. And eventually we'll just be left with some ashes and some hot air and some photons streaming off into space. And at this point, you can say with complete confidence that no one is ever going to work out what was in the book. So we've done. In practice, we have destroyed the information. However, in principle, just like the information about the fact that there was an egg that was about to fall was secretly present in all the positions and momenta of all the particles spreading out, if we kept track of all the heated up air molecules and all the molecules of ash and all the photons streaming off into space, kept track of every single thing, we would in principle be able to recover the information that was in the book. Like that would look slightly different. The correlations of air molecules and photon positions and everything be slightly different depending on whether that book was Twilight or some other book that had different writing inside it, even if the mass and so on were exactly the same. Okay, let's try option 3. We're now going to get, scale up our efforts considerably. Going to fly this book off into the spaceship, find the nearest black hole, and just drop the book into the black hole. And at this point, something weird happens, potentially. So at least according to Stephen Hawking back in 1975, what happens now is that the information will genuinely vanish from the universe. The black hole will eventually evaporate. There will just be a load of photons, but those photons will not contain any information about the state of the book. They will be in exactly the same noisy state, regardless of which book we threw at. So the claim that Hawking was making is something really quite profound. He was saying that at a fundamental level, quantum gravity is not reversible. That just looking at the state at some late time does not tell me enough information to be able to work out what the original state was at earlier times. This is the famous black hole information problem. Hawking was claiming that unlike ordinary quantum mechanics, then if information falls into a black hole, it's just gone for good. No way to get it back, even in principle. It's fair to say, I think, that this pretty immediately made a lot of people very unhappy. And there was a lot of responses, are you sure this is true? Because at stake was just a really very fundamental question of, is quantum gravity like every other law of physics we've ever known? Or is it something just fundamentally different in the most basic principles of how it behaves? So over the next 45 years or so, a lot of people made some increasingly compelling arguments that Hawking couldn't be right, that somehow secretly the information had to get back out. And this, in fact, became the dominant position in the field. The significant majority of people believed that this had to be the case, that Hawking's answer couldn't be right. But until 2019, what we didn't have was an actual calculation, an actual genuine gravitational calculation with a black hole and some Hawking radiation that says, look, this is information escaping. You can see it. Here it is. It's coming out. So every gravity calculation we did still seemed to say, no, it's just gone forever no matter what you do. That's now changed. A lot of work involving a lot of people, including me, but also a lot of others, have been able to do very precise calculations that show that information does come back out, that, Hawking's answer, if it's just lost forever, is too naive, that, yeah, it seems like it does come back out. But these new calculations create a new set of mysteries and questions and so on. We've resolved, or we know more than we did. We can answer a lot of questions that were just mysterious, open questions we had no idea about 3 years ago. But those very answers are creating new questions. So there's certainly not reached the end of the story. We certainly can't claim the problem has been solved, but we have made genuine progress. And it turns out the missing piece in Hawking's calculation, the thing that the effect, the physics that he wasn't including, is something that's almost too sort of pop science, science fiction, and so on to be right. It's something called space-time wormholes. So what are space-time wormholes? Well, in sort of Star Trek and so on, you have what are called spatial wormholes, where you have two distant regions in space that are connected by some shortcut that sort of exists at all times, but it's a shortcut between 2 points in space, and people can maybe travel through that or so on. And these are things that possibly could exist in the real universe. We have no real reason to think they do. But certainly, at least if you're not trying to be able to travel through them, if you're just trying to have a connection and people can meet in the middle, they're consistent with general relativity. But that's not what these wormholes are. These are something different. These are shortcuts between 2 points in space-time. So we have sort of position here 1 at time 1 here, have position 2 at time 2 here, and there's just a connection between just that point in space and time and this other point in space and time. So it's a temporary transient phenomenon. It's not something you can travel through or anything like that. But it's a contribution that you can include in calculations that it seems like should be there. And when you include its contribution, it resolves resolves a lot of the information problems. Although it does create these new problems, as I said. Okay, so that's my aim today. is going to be to try and give you guys some sort of vision, firstly, about what this information problem is. That's sort of roughly going to be the first half of the talk. And then what progress we've made, what we now understand that we didn't understand before. So I want to start with something pretty simple and sort of old, the original stuff that made people think black holes maybe had something to do with information and thermodynamics. That's this notion of black hole thermodynamics. So let's start with a simple question. Why is it that video I showed of the egg spontaneously unbreaking and jumping up in the air is not something that you ever see happen in real life? Eggs break all the time, particularly if you're me and you're very clumsy, but you never have some pile of egg splatter on the floor that decides to spontaneously jump up and form an egg. The answer is very simple. To make the egg spontaneously unbreak, we needed to reverse the velocity of every single particle. If we just missed a few, say 10 atoms or something, it's quite likely enough to make the egg just not reform. It will just, instead, the splatter will miss each other and it will, form a lump, but then splatter again into some new lump. So why is this? Well, it's because there's a very large number of possible states of a broken egg with, all slightly different positions and momenta for different particles, but they all look basically like a splattering broken egg to us. They're macroscopically indistinguishable. They all look physically pretty much the same, but microscopically they're distinct different states. Because the laws of physics are reversible, when we evolve backwards in time, each of this incredibly large number of broken egg states needs to end up in a distinct physical state. But there just aren't enough distinct physical states of an unbroken egg to be able to have that happen more than a tiny fraction of time. So the overwhelming majority of splattered egg states will not reform into an unbroken egg. It's only some tiny, tiny fraction that will. We can quantify that in a very nice way, and this is the notion of entropy in thermodynamics. We just say that the entropy, the log of the number of microscopic states that look macroscopically indistinguishable of a broken egg is much, much bigger than the entropy of an unbroken egg. And so in practice, we will, it's very rare to have a evolution that goes from a state of larger entropy to a state of smaller entropy. We have the second law of thermodynamics. Entropy always increases. So already we're seeing that even ordinary physics, which fundamentally we know is microscopically reversible, appears to be irreversible. There's going to be, the whole point of this talk is going to be trying to see that that's also true about black holes. The apparent irreversibility is an illusion, and that really secretly it's microscopically reversible. Okay, so let's now turn to the stars of our story, black holes. So the dynamics of black holes, it turns out, is also pretty irreversible. So on the right, we had a figure of two black holes merging. That's a simulation for LIGO data and stuff. So black holes can merge if they get close together. Their gravitational pull pulls them together, but they can never unmerge. So this is already an example of an irreversibility in their dynamics. And in fact, they obey this beautiful theorem that was found by Hawking, just that the total area of the horizons of all black holes increases over time. This is the surface area of the horizon. It's like a sphere in space, and it's the total area when you add up all those spheres can never decrease. This looks an awful lot like the second law of thermodynamics, right? We have some quantity, entropy in one case, area in the other, that's always going up over time and creating this irreversible dynamics. Of course, at this point, you would very reasonably say that this is just some coincidence. It's not that weird to have a theorem about something monotonically increasing over time. But it turns out there are other laws of black hole thermodynamics that correspond to all the other laws of sort of ordinary thermodynamics. I'm not going to go through them all in detail, but the basic idea that people showed is that if you take everything in ordinary thermodynamics and replace entropy wherever it appears by something proportional to horizon area of the black holes, and you replace temperature whenever it appears by something proportional to something called the surface gravity, which is just a particular property of the black hole horizon, then all the laws of ordinary thermodynamics get mapped into true laws about black hole dynamics. I should say the reason I only say proportional to here rather than giving you exact numbers is that all these laws stay exactly the same if we say replace surface gravity by surface gravity divided by 2, and at the same time replace area by 2 times area. The laws are invariant if we simultaneously rescale the two quantities. So there's not enough information to sort of nail down the exact analog of T and of S, of entropy and temperature. It can just get it up to a constant of proportionality. But even so, this is starting to feel like a pretty damn big coincidence. But you still might say it is a coincidence because we still have one very, very big problem. And that's that if we have some ordinary thermodynamic object with any non-zero temperature, then as a very general principle, it should radiate energy over time. It should emit photons, give out radiation, and gradually lose entropy and cool down. But as sort of everyone knows, famously, nothing can escape the black hole. That's the whole definition of having a black hole. Things can't escape. And so there shouldn't be any way for a black hole to radiate energy. Just nothing can come out of it. That's sort of the central feature of the black hole area theorem. However, here is where Stephen Hawking made possibly his most profound and beautiful contribution to physics. So what he showed is that it's somehow, if you add in quantum mechanics to your classical gravity with black holes just sitting there not being able to have anything escape, then it turns out that they do radiate photons. They do emit radiation. It's called Hawking radiation. And it has a temperature that is indeed proportional to this surface gravity kappa. Or over here, it turns out it's proportional to 1 over the mass of the black hole. Generally, the mass of realistic black holes is very, very big. So this temperature is really, really, really tiny. For astrophysical black holes, it's maybe nanokelvin or less, much colder than the temperature of the universe, cosmic microwave background temperature, but it is a non-zero temperature. It exists. And this formula is it's really one of the deepest contributions to physics we've ever made. And you can see that actually just by looking at the form of the formula. So it really has to, just to be able to make sense of this formula, you have to bring together basically all the fundamental areas of physics, right? We have a speed of light cubed in here, right? That tells you that some way special relativity, relativistic effects are involved in this calculation. You have a Newton's constant, G Newton, that tells you that the gravity is obviously getting involved in the black hole. You have an H bar that tells you it's a quantum effect. If we have no quantum effects, take H bar goes to 0, then this temperature goes to 0. You have no radiation, as I claimed before. We have a Boltzmann's constant, so there's thermodynamics getting involved. Obviously, it's the temperature, right? So we have relativity, gravity, quantum mechanics, thermodynamics, and of course we have a pi getting involved. So there are circles getting involved in this thing somehow. So this is really giving together all the fundamental fields of physics. And now that we sort of have this precise answer for the temperature, we can just match the laws of thermodynamics and we get an answer for the entropy, which in nicely chosen units says that it's just the horizon area divided by 4 times Newton's constant. So this factor of 4 is very specific factor that yeah, it's sort of extraordinary. You can work it out, but you can. And this is the famous Bekenstein-Hawking entropy of a black hole. It's worth noting, by the way, that the area theorem I claimed before, that the area of horizon black hole always increases, is no longer true once we have this quantum effect. Instead, it's just subsumed into the broader second law of thermodynamics. So a black hole can evaporate, it can lose energy and get smaller, but the decrease in entropy of the black hole when that happens is more than matched by the increase in entropy of Hawking radiation. So the total entropy of the universe still increases over time, consistent with the second law of thermodynamics. Okay, so I want to just give you a flavor of the sort of physics getting involved in Hawking's calculation. I'm certainly not going to do it properly. That's well beyond the scope of this talk. But to talk about it at all, we need to talk a bit about quantum mechanics. And quantum mechanics, very, very famously, is weird, right? And possibly the most important way that it's weird is the phenomenon called quantum entanglement. What this means is that you can have well-defined, precise quantum states. You can know everything about the state of a system that it's possible to know. But if we break that system up into constituent subsystems, then the states of those subsystems can be inherently noisy, inherently uncertain, even when the state of the entire system is known. So that's something that classically can just not happen. If I have two classical particles and I know the combined state of the two particles, then I must know the individual states, the position, the momentum, so on, of each individual particle. That's just what it means to know the combined state of the two particles. But that's not how it works in quantum mechanics. You can have these entangled states where this is an entangled state on two qubits. So two quantum systems that can either be 0 or 1. And it's a well-defined state on the two systems. But if we look at the state of one of those systems on its own, then it's just a 50% chance of being 0 and a 50% chance of being 1. It's just not well-defined. So yeah. So the sort of amount of subsystem uncertainty in these entangled states can be quantified by a certain sort of entropy, right? Entropy just means something measuring uncertainty. And that uncertainty is called an entanglement entropy. So that's quantifying the amount you don't know about the subsystems, despite knowing the exact state of the entire system. I really want to emphasize that this is a different notion of entropy from the entropy that appears in the second law of thermodynamics. That entropy can exist classically. It's just our uncertainty about the state of the system because we don't know the exact state. We only know the macro state. We only know roughly what it looks like. But the state can still be perfectly well. The microscopic state can still be well defined. We just don't know it. In this case, the state of the subsystem isn't even defined at all. It's just not a meaningfully well-defined thing. Okay, and then there's going to be one more property that's going to be important for us, that if we split the system into two subsystems, then the entanglement entropy of both those subsystems is always exactly the same. It's an uncertainty sort of shared between the two, rather than different ones for each of the two. And that's true unless the state of the sort of global system is itself noisy. As long as the state of the entire system is well defined, then the two subsystems have to have exactly the same entanglement entropy. Okay, so now let's add black holes into the story. Okay, so believe it or not, this very crude diagram represents a black hole. It's physicists drawing of a black hole. So what does this represent? It's called a Penrose diagram. And basically, as you go upwards on this diagram, that means you're going into the future. Okay, that represents points in the future in time. As you go to the right, that means you're going to larger radius in this spherically symmetric black hole. And you might say, well, there's two more directions in space-time, the angular directions, the sort of theta and phi. We're just not going to draw them because we're going to assume everything's spherically symmetric, and so nothing's interesting will happen with them. And unfortunately, I don't have a 4D PowerPoint slide to show you. So we're just going to restrict to these two directions. Okay, and the way this diagram works is that distances are not at all to scale, except for the fact that light rays, the speed of light is exactly 45 degrees. So something traveling inwards at the speed of light will travel at 45 degrees in this direction, or 45 degrees in this direction. Something going outwards at the speed of light will go this direction. Okay, so the things are so not to scale that these lines out here actually represent infinitely far away from the black hole. So that's sort of one important point in the diagram. This is infinitely far away from the black hole. There's sort of no, that just looks like ordinary flat space with no gravity or very little gravity out there. There's a second important point, which is this wiggly line up here. So this is the so-called singularity of the black hole. Okay, it's in classical general relativity, it's the point where the curvature of space-time becomes infinitely strong. Everything becomes nonsense. And I've said here be dragons and drawn got a picture of the dragon from Game of Thrones, because all we can say about this point is that the classical space-time description is just breaking down, and there should be quantum effects that become very important, but we don't have any way to get control of those quantum effects. We just don't know the rules of the game anymore at this point. It's just, we have no idea. We would need some complete theory of quantum gravity to make any progress at the singularity. So nothing I'm going to say in this talk is going to say anything directly about the singularity of the black hole. But there's a final important thing on this diagram, and that's the famous black hole horizon, event horizon of black hole. So what is this? Well, it's a 45-degree line going out to the right. It's the last point at which, if you start heading outwards at the speed of light, you can escape off to infinite radius rather than ending up just hitting the singularity. So it's the last moment at which you can escape the black hole. And at least for very large black holes, we think, based on very fundamental reasons, that the sort of classical description of space-time should be very trustworthy at the event horizon. There's nothing crazy going on there. Like locally, it looks pretty like flat space for a big enough black hole. It's very, we should be able to do controlled calculations of the horizon without having anything go too crazy. And that's what we're going to do to see Hawking radiation. So we're going to have some quantum effects going into play, but those quantum effects are just going to be that we're going to have quantum mechanical fields that are going to propagate in this classical space-time background. We're not going to have to deal with space-time itself in a quantum way, which is, of course, the thing we famously don't know how to do. So that's very good. That's going to let us actually calculate things. So in the universe, there are a lot of quantum fields. There are electromagnetic fields and so on. These need to be quantized. And we're just going to study these in this background. And it's a fact about quantum field theory that if we look at some fields at a point x, and we look at fields at a point x plus epsilon, then the degrees of freedom describing the state of those fields are going to be entangled with one another. That's just always true. It's true for any state in quantum field theory. It's true for the vacuum state where you don't think there's any actual particles there or anything like that. There's always this entanglement between fields. So this has nothing to do with black holes, but in particular, it will be true for a black hole horizon, right? A black hole horizon is a point in space-time. We can have fields slightly outside the black hole horizon, and they'll be entangled with fields slightly inside the black hole. So these red things represent just entanglement of those fields. But these are not actual particles. They're just vacuum entanglement between different points in space. However, because we have a black hole, then as we evolve these fields forwards in time, we see something very interesting happen. The fields that were sort of just inside the black hole, say they're electromagnetic fields propagating at the speed of light, will always have to remain within the black hole because there's just no way for them to escape. On the other hand, the fields that were slightly outside the black hole, when they travel outside of the speed of light, they are able to escape. So they end up all the way out at asymptotic radio infinity, way, way, way away from the black hole. So this very short range entanglement, which is always present in quantum field theory, has got pulled apart. And we've ended up with very, very long distance entanglement between stuff way out near the asymptotic infinity, far, far away from the black hole, and stuff inside, still stuck inside the black hole. So this stuff far away from the black hole ends up being this famous Hawking radiation. And what we see is that the Hawking radiation is entangled with the stuff inside the black hole. And so that's why Hawking radiation is inherently noisy, because it's inherently entangled with stuff inside the black hole. Of course, this process doesn't stop. As we look at fields that start closer and closer to each other near the black hole horizon, then they take longer to get spread apart by the black hole dynamics and for the stuff outside the horizon to escape. But eventually it will. So over time, you get more and more Hawking radiation. The amount of Hawking radiation just sort of linearly increases with time as more and more radiation escapes. And so this entanglement between the Hawking radiation way, way, way away from the black hole and stuff inside just seems to increase linearly forever. It goes up and up and up and up. But now something weird happens, because eventually this entanglement entropy between Hawking radiation and the interior of the black hole is going to become larger than the Bekenstein-Hawking entropy of the black hole itself, right? The Bekenstein-Hawking entropy is just proportional to the area of the black hole. That's getting smaller over time. The entropy of the Hawking radiation, the entanglement entropy of the Hawking radiation is getting bigger. At some point, they're going to cross over. We call the time when that happens the page time, after Don Page, who was the first person to realize its importance. And very importantly, when this happens, the black hole is still pretty big. It's roughly half the size it started with, but it's still, macroscopic in size. It's some big thing. And so our calculation is still under control. We still have some pretty smooth classical space-time near the black hole horizon. So we should be able to trust this Hawking's calculation then. But it says that this entanglement entropy is just going up and up and up. Now, whether this is a problem depends on what you think the Bekenstein-Hawking entropy of a black hole is. But the most natural interpretation, the sometimes called the central dogma of black hole physics, the one that makes the most sense of the second law of thermodynamics, is that it's an entropy in the same sense as the entropies that appear in the ordinary second law of thermodynamics. It's what's called a statistical entropy. It's just counting the log of the total number of possible states that a black hole can be in. So this is true in string theory and ADS CFT and so on. Some people don't believe it's true in other theories of quantum gravity that maybe aren't as well defined. But I would say that the majority position is that this is probably true, that this is the most natural thing that this Bekenstein-Hawking entropy seems to be computing. And if that's true, then we now have a paradox with this entanglement entropy of the Hawking radiation becoming bigger than the Bekenstein-Hawking entropy. Because I said before that if the global state is still well defined, if we haven't lost information, then the entanglement entropy of the Hawking radiation has to be equal to the entanglement entropy of the black hole, right? Because that's they're the only two systems that we have. But then it would be saying that the entanglement entropy of the black hole is bigger than its statistical entropy. So our uncertainty about the state of the black hole that's just inherent from having this entanglement is bigger than the uncertainty from just not knowing anything about its state. That's obviously impossible, right? If you don't know anything about the state, that's like the maximum amount of uncertainty you can have about it. You can't have even more uncertainty than that. So we now have a paradox. And if you believe this central dogma of black hole physics, there's only two options for resolving it. The first is just that information has been lost. The global state is no longer well defined. It's just inherently noisy. The dynamics is not reversible anymore. The second is that something has to have gone wrong with our calculation of the entanglement entropy. At or before this page time, the entanglement entropy has to stop going up and started going down so that it remains below this Bekenstein-Hawking entropy of the black hole, which is going down over time as it evaporates. Okay, so Hawking's answer would just say it just goes up and up and up like this. But to make it consistent with information being lost, it needs to, maybe it could start going down here instead, but the general consensus is that it would probably start going down pretty much exactly here and just stay bounded by the Bekenstein-Hawking entropy of the black hole. So this curve that goes up and then down for this amount of inherent uncertainty about the state of the radiation from its entanglement is called the Page curve. Again, it was introduced by Don Page. Turns out that if this is going to happen, if this entropy is going to start going down, uncertainty start going down, then the Hawking radiation needs to start having information about stuff that goes into the black hole. And it needs to start having it exactly here. It can't be informationless anymore. Okay. So I've now sort of laid out, what the situation was maybe 2-3 years ago. We're now going to see how these space-time wormholes are going to save us and fix the story and let us see information coming out. Okay, so there's a small possible loophole, you could say, about Hawking's calculation, which seemed very, very reliable. But yeah, maybe it doesn't know everything that's going on. And the reason for that is that what Hawking is calculating is what's called a density matrix. It's characterizing this noisy state of the Hawking radiation. And you have different elements that characterize different aspects of the matrix. And in principle, Hawking's calculation can calculate any of those elements for you. But this matrix is really, really, really big. There's a lot of states that the Hawking radiation can be in, like e to the entropy of the radiation. And that's roughly the size of the matrix. So it's an e to the s by e to the s matrix. That's absolutely huge. If you have a really, really big matrix and you make tiny changes to each of those, the elements of the matrix, so changes of size e to the minus s to each of the elements, then you can still completely change the properties of the matrix. For example, you can completely change its entanglement entropy. So we don't really have good control over this calculation. We have good control over the individual elements up to tiny errors. But if we actually think about the matrix as a whole, then those tiny errors can add up when we look at all the different elements separately. And so they can completely change what happens when we look at other properties of the matrix. Okay, so maybe the entanglement entropy of this matrix is actually very different to what Hawking thought it was. How can we resolve that? Well, the obvious answer is just to compute the entanglement entropy directly, right? Rather than calculating this ridiculously large matrix and then calculating the entanglement entropy from that, let's just try and do one calculation that directly says this is the entanglement entropy. However, we have a problem here because the entanglement entropy is not an observable in quantum mechanics, not something you can measure. And so that also means there's not a calculation we can do involving a sort of single copy of a quantum state that will tell you what the entanglement entropy is. There's a sort of classical version of this same problem, which is, let's say we have some probability distribution, and we want to know whether this probability distribution is deterministic, i.e. it has p equals 1 for something and 0 for every other possibility, or if it's noisy. If we're only allowed to look at a single sample from this probability distribution, there's no way for us to tell, because we get some sample, it's some particular thing, and that doesn't really tell us anything, right? It doesn't tell us if it always has to be that particular thing, or if it could be, if it's just totally random, or somewhere in between. However, there's a simple solution to this, which is just to look at multiple copies of the state. Let's say we sample 2 times from this probability distribution. If it's not noisy, we'd have to get exactly the same thing both times. If it is noisy, we probably don't. So if we sample 2 times, so we have a dice and we want to know whether it's loaded or not, right? We roll that dice, we get a 5. Doesn't tell us anything about whether it's loaded. But if we roll it twice, get a 5 both times, that's a tiny bit of evidence that maybe it's more likely to be loaded. If we rolled it 100 times and got 5 every time, then we're really starting to be confident this is probably a loaded dice. Okay, so formally what you want to calculate is this probability of getting the same state both times you sample from it, right? This is sum over all possible outcomes of the probability of getting that outcome squared. Okay, there's a quantum analog of this thing, which is just the trace of this density matrix squared. The density matrix is like a probability distribution for quantum mechanics. So if the state is unentangled, if there's no uncertainty about the state, then this will have an answer of 1. We always get the same state. If it's entangled and so there's some inherent uncertainty, then it will be smaller, right? The chance of getting the same state will be much smaller. Okay, so we're going to try and calculate this trace of rho squared, and magically we're going to get an answer that gets smaller and smaller and smaller until the page time, and then it starts getting bigger again. So that's telling us the uncertainty starts going down after the page time. How are we going to do this calculation? Well, basically the only way we know how to do quantum gravity uses something called a Feynman path integral, which is this famous story where in quantum mechanics you can work out how to calculate things by just sort of integrating over all allowed configurations. So if you have a single particle, you can integrate over all possible paths that particle could be taking through space. And then you weight all those paths by some factor, e to the is, where s is the action of the path, integrate them all, and just the total answer just can then read off the answer you want. So for gravity, what are the configurations that we want to be integrating over? Well, the dynamic gravity is the dynamics of space-time itself, right? The geometry of space-time. So we should be sort of integrating over all possible geometries of space-time. And in fact, we also want to sum over all possible topologies of space-time. So that's also dynamical in gravity. Okay, so we're going to do this for traces rho to the squared. And it turns out that there's going to be two configurations that are going to be important, right? Normally, this Feynman Particle integral ends up being dominated by a couple of simple contributions that sort of look like classical solutions obeying some classical equation of motion. So the first solution just looks like two black holes, right? We have two copies of our state, so we just have two independent black holes, and we have the Hawking radiation from him, and then we measure the probability of the Hawking radiation being in the same state. And this indeed gives the Hawking answer. It just gets smaller and smaller and smaller over time, suggesting that the Hawking radiation is getting ever more noisy. But there's another configuration. And in this configuration, the two black holes are connected together by a space-time wormhole. So this is some crazy, wacky quantum mechanical, it's roughly speaking analogous to some quantum mechanical tunneling effect between the two black holes, but it's some configuration that should be in there. And this one starts off really, really tiny. Roughly, it's like e to the minus the Bekenstein-Hawking entropy. But as the black hole evaporates and gets smaller, it becomes easier over time, in fact, to connect the two together using a space-time wormhole. So it gradually increases over time as the black hole evaporates. And what happens is that after the page time, this thing starts giving a larger contribution than this ordinary thing that was giving the Hawking answer. So this tells us that after the page time, the uncertainty of the Hawking radiation starts going down. I should say that this thing trace of rho squared is a pretty bad measure of uncertainty. It turns out it's not particularly well behaved. What we really want is this entanglement entropy that I mentioned before. So this entanglement entropy, one way to calculate it is as a derivative with respect to n of trace of rho to the n when n is equal to 1. So how are we going to compute this thing? Well, that seems a bit harder, right? Because if n's sort of a non-integer value, then we have a non-integer number of copies of the state, and that doesn't even really make any sense. But for integer n, it turns out that after the page time, then this trace of rho to the n quantity ends up being dominated by a sort of multi-boundary space-time wormhole where you have all these different sort of black holes. You have n different black holes, and they all get connected together in the middle by one big sort of blob, one big like octopus-like thing. And this n-boundary space-time wormhole thing has a symmetry. It has a symmetry where we spin it round and push this boundary to this boundary, this boundary to this boundary, and so on. So what we're going to do is do a very clever trick. We're going to quotient this whole n-boundary geometry by this symmetry that rotates them round. So we're just going to look at sort of one little wedge here, where we go just from one boundary to the next boundary over, and then we're going to take the edge here, and we're just going to glue it directly onto this bottom edge here. So rather than having n separate boundaries, we now only have one boundary. We're looking at the sort of, the quotiented version of what's going on. This geometry looks a lot more like the geometry we had when we just had a single black hole, right? Where in Hawking's calculation, for example. But it has something a little bit weird. And that little bit weird thing happens at this point at sort of the tip of the wedge. So let's say we go in a little circle around the point in the tip of the wedge. So we start here, we go around it, and then we get a little way around, and then this gets glued onto the bottom. So we're already back where we started. So what this means is that the sort of circumference of the circle, rather than being 2 pi r, it's just 2 pi r divided by n. It's a much smaller circle than you might think. This is what happens if you have a cone and you draw a circle around the tip of a cone. So it's called as conical singularity. So rather than thinking about this n boundary solution, you can just think about a one boundary solution with a conical singularity of strength with an angle around it, opening angle around it of 2 pi over n. Now there's no reason that n needs to be an integer. So now we've thought about this different geometry, we can just analytically continue to some non-integer value of n and just gradually tune it and end up taking a derivative at n equals 1. Magically, at n equals 1, there's no conical singularity anymore because the angle around it is 2 pi, which is just ordinary non-singular space. And it turns out that this means that the entanglement entropy that we get ends up just being given by the area divided by 4 times Newton constant, which should be familiar from the Bekenstein-Hawking entropy earlier, of a particular surface in the original black hole spacetime that appeared in Hawking's calculation. So this is kind of magical. There's something called a particular surface called quantum extremal surface that just obeys certain equations that you can solve. And it's really magical because these actual n-boundary wormhole solutions you can actually only find in really, really simple toy models of a black hole. In realistic 4D black holes, you actually can't find the explicit wormhole solutions at all. But you can find this special surface that ends up being the only thing that matters when you care about the entanglement entropy. This complicated analytic continuation of these solutions we couldn't even find ends up being something that we can find and calculate and make precise answers. So what are those answers? Well, it turns out that the surface, the special surface that sort of controls the entanglement entropy you get from this wormhole calculation sits just inside the horizon of the black hole. It's a Planckian distance, in fact, inside the horizon of the black hole. And in fact, its position on that horizon changes with time as we sort of collect up more Hawking radiation, as we look at the uncertainty, the entropy of more and more Hawking radiation, tracks along the horizon going sort of up into this corner. What that means is that its area gets smaller as time as the black hole evaporates, because the black hole is getting smaller in time as it loses energy. And so what we find is that we get that the entanglement entropy of this Hawking radiation after the page time is exactly this Bekenstein-Hawking entropy, this horizon area of the black hole. So that's exactly the prediction that was made of what needed to happen if information wasn't going to be lost. And it's exactly what we're finding by just doing an explicit calculation of the entanglement entropy directly, which sort of Hawking never did, but if he did, he probably wouldn't have noticed the space-time wormhole contributions. Adding them in means rather than seeing information being lost, we're seeing information coming back out, or at least the uncertainty of the Hawking radiation, the entropy of the Hawking radiation going down. Okay. However, if I said that if this is going to be happening, if information is not going to be lost, we also need to see information start coming out of the interior of the black hole after the page time. Okay, not only does the uncertainty of the radiation need to go down, but the radiation needs to be in a different state depending on the state of stuff that we threw into the black hole. So how are we going to see that? How are we going to see that this Hawking radiation can be used to recover information about stuff that got thrown into the black hole? How can we learn what was in twilight? Well, in an ideal world, we just sort of have a prescription for what the exact microscopic dynamics of the black hole are. And then, there would just be some formula for what the exact state of the Hawking radiation ends up being. And we just sort of be able to directly see that. But those dynamics are expected to be very, very complicated. We'd need a complete theory of quantum gravity and so on. That's just too hard for us to do right now. So as usual, we do what physicists do best, and we're going to cheat. And we're going to try and work out the answer of whether you can extract information without seeing exactly how the detailed form in which the information gets out. Turns out, people have thought a lot in the last 20 years about how you can recover quantum information that seems like it might have been lost. And the reason they've been thinking about it is because of quantum computers. So with quantum computers, you need to be able to do something called quantum error correction. Quantum computers will be noisy, and you want to not have that noise mess up your calculations. You need to be able to correct the errors that show up. And so people developed a whole set of tools that can let you know how to recover for any arbitrary dynamics. They'll tell you how to recover information. And roughly speaking, the way that they do that is you imagine some quantum computer that simulates the noise process itself, that basically simulates forming a black hole and then evaporating it, and then compares notes between that simulation and the actual state it has, and uses that to learn about what the input state was. So that's a very crude version of the story, but that's roughly how it works. And you can do this calculation. You can do this calculation in gravity, and in a total crazy, almost nonsensical answer, what you find is that information does escape, and it escapes through a space-time wormhole that connects the actual real physical black hole to the simulation of a black hole that you have in your quantum computer in order to try and recover this information. So that almost seems like total nonsense. And certainly there's questions about how literally we should take it, but you do the maths and that's what comes out. And in particular, this sort of wormhole solution only dominates. You only see information coming out if you're after the page time. So that exactly agrees again with our predictions that Hawking radiation would carry no information before the page time, but then after the information, it would start encoding some information about the stuff that fell in. I should say that I lied quite a lot on the previous slide. I really oversimplified the story. And in fact, just like our calculation, the entanglement entropy, really we need to do an analytic continuation in the total number of simulated black holes and take a limit where the number of simulated black holes goes to 0. So it's actually a lot messier than that, but that's how the maths works, at least. Of course, if you're actually a person with a quantum computer and you want to do this, you can't just analytically continue the circuit, the algorithm you're using to solve the problem. So that's just a sort of mathematical trick. If you actually want to get the information out, the best way of any algorithms that are currently known uses something called Grover search. It's one of the 2 quantum algorithms that like anyone uses for anything. And it turns out this that actually involves simulating the black hole, not just once, but exponentially many times. Exponential in the entropy of the black hole, which is itself order 10 to the 70 or so for real life black holes. The time it's taking is e to the 10 to the 70. This is an utterly impossible process to actually do in practice. So even though Hawking at some level was wrong and fundamentally the information does come out, then for all practical purposes, Hawking was completely right. From a computational complexity point of view, Hawking was 100% right. But let's just talk a little bit. I'm getting near the end of my time, but I do want to say a little bit about exactly what information escapes and why, because you can make very precise predictions about it that agree with previous predictions people have made. But basically, when you do this analytic continuation in the number of simulated black holes, just like for the entropy calculation, all this complicated stuff about wormholes end up boiling down to a calculation of this special quantum extremal surface, this special surface in the space-time. And basically what happens is that any information that is to the left of this special surface can be pulled out through a wormhole and it can be decoded by your quantum computer. Anything to the right of it just can't. There's no information yet about it in the Hawking radiation, and we can't learn any information about it with our quantum computer. Okay, so I just claim to you that that's true. And there's a fancy name for this sort of green region to the left of this surface. It's called the entanglement wedge of the Hawking radiation. But it means stuff that can be pulled out through a wormhole by someone acting with a quantum computer on the Hawking radiation. Okay, so let's say we throw a diary or twilight or whatever into the black hole. And let's say we do it after the page time. So information is already starting to come out. Initially, we can look at sort of where this diary goes as it falls in this space-time. And the answer is it goes in the blue region to the right of this quantum extremal surface. So that means the information in the Hawking radiation is not yet, so the information about the diary is not yet in the Hawking radiation, which is good because the Hawking radiation had already come out of the black hole before the diary fell in. So that's sensible. But then let's say we take a bit more Hawking radiation. We let the black hole evaporate a bit more, collect up a bit more radiation. Well, then what happens is that the quantum extremal surface moves. It moves along the horizon, like I said earlier. That means this green region is now bigger than before, the stuff that can be pulled out through a wormhole. And now the same sort of path of the diary now goes to the left of the quantum extremal surface, goes through the green region, and it can be pulled out through a wormhole. We can learn what was in the diary just by looking at all the Hawking radiation. Turns out the time you need to wait something called the scrambling time of the black hole. It's actually incredibly short. It's like order seconds for a realistic black hole, compared to the time for the black hole to evaporate, which is billions upon billions of years. So it's really, really, really fast that the information comes back out. And amazingly, this exact prediction of this exact scrambling time, like up to the exact coefficient in front of it, was predicted back in 2007 by my PhD advisor, Patrick Hayden, and John Preskill. And they made that prediction just based on very simple time models, where you just assume that the black hole is an ordinary quantum system where information is lost, and you just see what happens with ordinary quantum systems and that have certain properties. And you can just make this precise prediction from that. And yeah, we can now do a gravity calculation that gets exactly the same time on the nose for how long you need to wait before the information comes out. There's also a load of other stuff that these calculations resolve. So some of you, if you were listening to colloquiums by people like me back around 2012, you may have heard a lot about something called the Firewall Paradox, the idea that there needs to be a like wall of energy at the black hole horizon if information is going to come out. And the way this works is very simple. If the entropy is uncertainty of the Hawking radiation is going to be going down over time, then this sort of late time Hawking radiation needs to be entangled with the early Hawking radiation. But we also said earlier that it needs to be entangled with this interior partner thing, this mirror image mode across the event horizon. And there's a famous theorem called monogamy of entanglement that one quantum system can never be simultaneously entangled with two different systems. So how do these calculations sort of resolve that tension? Well, it's very simple. We can just evolve this interior mode back in time. And what we see is that it was actually previously in this green region here. And that means that it can, we can act on this earlier radiation and pull this interior mode out through a wormhole. It means this interior mode was secretly the same degree of freedom, or a degree of freedom acting on the early radiation all along. So it's not one quantum system entangled with two different systems. It's one quantum system entangled with two different descriptions of the same quantum system. So there's no problem there. I should say there's a load of subtleties here I've skipped over, but magically it all works out at a precise mathematical level. There's various corrections that cancel out and so on, and everything works out beautifully. Okay, so that's really all I want to say. I've said everything about what we now know. There's all these big questions. How do we see the information come out? How do we see the entropy go down? How do we have a story that resolves the firewall paradox, if not a complete resolution of it? And they're now all answered. But there is a problem, which is that these calculations raise a whole heap of new questions. And basically, the problem is that including these space-time wormholes clearly seems to be the right thing to do. It's the natural thing to do from a first principles point of view. And it keeps giving us sensible answers to these questions that have haunted us for the last several decades. But they also cause a load of new problems. So just to give you one example of them, so there's a quantity called the black hole spectral form factor, that if you calculate it naively in gravity with no wormholes, it just gets smaller and smaller and smaller until it goes to zero. Which is something that's impossible for a finite entropy system. Instead, it should get really, really small and then sort of fluctuate about the bottom with some little noisy progression. So if you compute the square of this spectral form factor, you now have two copies of the black hole. You find a contribution that has a space-time wormhole connecting them. And this is non-zero even if you look at very late times where it seems like it should decay to zero. The non-wormhole contribution decays to zero. So this is great. It solves our problem of it seemed to be decaying to zero when it shouldn't be. But there's something very weird here because we've calculated a quantity squared and it was non-zero. But if we just calculate the quantity itself, we get something that's zero. So this sort of doesn't make any sense at all. If you think of this gravity as encoding a sort of single set of microscopic dynamics, and instead it sort of looks like gravity is computing an average over all sorts of different microscopic dynamics. In this case, the wormhole contribution is telling you the difference between the sort of average of z squared and the square of the average of z, right? These are not equal to each other in general because you have some noise. And this is what the wormhole contribution is giving you. So in sort of very simple time models and sort of 2D and stuff, this is explicitly true. We can show it's true, but we have no idea if it's always true or if it's just a feature of these very simple time models. So that's the sort of new big mystery that maybe is going to haunt us for the next few decades, until someone resolves it nicely in some way. Okay, so let me just end on some very final excited, hypey sort of comments, which is that sort of everything I've told you about today, the fundamental conceptual framework I was using is just semi-classical gravitational path integrals. And these have been around, this sort of framework has been more or less understood since before Hawking radiation was a thing. It's basically the framework in which you have Hawking radiation. However, the actual tricks and tools and these analytic continuations and stuff that I used that gave the right answer were developed over time, and they were developed in the last 10 years mostly as part of something called the sort of it from qubit program of understanding information in what's called ADS-CFT, particular theory of quantum gravity. That in turn came out of the discovery of ADS-CFT in the late 90s. ADS-CFT was discovered by looking at like branes and dualities and stuff in string theory and seeing that it should be true in string theory. And of course, that came out of the development of perturbative string theory in the 70s and 80s. And in fact, the original reason people cared about perturbative string theory was that they cared about nuclear physics. So this whole story that really is just about semi-classical gravitational path integrals, if you track it back far enough, the discovery of how to do it came out of people trying to do calculations and explain calculations in nuclear physics, which sort of is beautiful to me in a weird, ugly way, right? The fact that we had to take this incredibly roundabout route to get the right insight to then make progress on something. We really had decades of like gradual developments in different areas and not so gradual developments, really like transformative developments. And eventually those add up and suddenly something that just seemed totally beyond us becomes actually a doable calculation if you're thinking about the right set of ideas. So yeah, quantum gravity is really, really hard. We're not going to solve it anytime soon. But I genuinely do believe that there's like real progress being made, that we're not just off, chasing shadows. There's real concrete progress being made over time. So yeah, thanks for listening.
So thank you very much for this very clear talk. So we have time for questions. So if you have questions, please raise your hand so that I can identify you. But maybe while people are thinking about questions, maybe I can start. So you discussed the possibility of extracting information about black holes, and in particular, you showed the entanglement wedge, and that includes a portion of the singularity. So can you really extract information about the singularity, or how close to the singularity can you go?
Yeah, great question. The answer basically, so yeah, the entanglement wedge is this green region. It's the region that can be pulled out through a wormhole. The answer is not really, for two reasons. The first is that we only know how the calculation works in semi-classically, basically. It only makes sense semi-classically. And as you get near the singularity, then the semi-classical physics will break down, the classical space-time will break down, and we don't have the tools to do the calculation there. Basically, there's a problem that when you do the calculation, if there's some dynamics happening in this green region, you need to know what those dynamics are before you can know how to do the reconstruction, right? Because basically you need to undo those dynamics, and then you can work out how to pull it out. And so if you don't know the dynamics up near the singularity, then you don't know how to deal with stuff up there, is the short answer.
Okay, thank you. So I can see a hand raised. Daniel Thompson, please go ahead.
Thanks, Mark. Thanks for the nice talk there, Geoff. You mentioned in the toy model that you could explicitly find these multi-boundary geometries, but not in realistic gravity.
Yep.
So can the existence of such saddles with the right properties be proven, even if the particular solution isn't known or can't be found explicitly?
Yeah, so roughly speaking, yes. So we certainly know there exist solutions with the right topology. And essentially the existence of this quantum extremal surface is a signal that there exists, that the solutions exist. We very strongly, we have every reason to think that the solutions do exist and no reason to think that they don't. It's just, higher dimension, like 4-dimensional black holes, you have a lot of gray body factors and stuff like that, and the physics is a lot messier.
But in principle, some numerical GR colleagues of ours could, go ahead and.
In principle, there's no reason why they wouldn't be able to. Yeah, like we can find more things. We can find more solutions numerically than we can find analytically. So yeah, it's just a matter of computing power essentially. There's a problem of because these are solutions for classical gravity with quantum fields that you then need to integrate out the quantum fields. So you would need to do the quantum field calculation to do it all numerically. You'd need to combine some like lattice, like QFT calculation with like GR calculation. So in practice it might be quite hard. But there's no fundamental obstruction to doing something like that.
Thanks.
Okay, any other question? Well, then maybe I can ask another one. So if there is an inner horizon and the singularity is time-like, is the computation going in the same way, or you don't have to worry about this because this would be unstable and only space-like singularities are important?
The quantum extremal surface will be near the outer horizon. I think there's very good reasons to expect that the inner horizon will be unstable and nothing beyond that makes sense. But I don't think we'd be able to say anything more about the inner horizon than we can say about the singularity, really, because you have the same problems of you lose control over the calculation.
Okay.
There's a question in the chat, I think. So yeah, a question in the chat is, what if a wormhole connects a black hole with a white hole and not two black holes? So some information entering the black hole will be released out of the white hole. Yeah, so to some degree, you could probably think of that as being what's happening, because you have backwards time evolution in the calculations. You have backwards time evolution going on as well as forwards time evolution. And in the backwards time evolution, it is a white hole. So from some point of view, then there's not much difference. It's just a matter of like convention, whether you're calling it a black hole or a white hole, or what time direction you're evolving at any given time. I think that would be my answer to that question.
So your computation is Euclidean, or?
Well, it's analytically continued Euclidean computations. You can also try to, the quantum extremal surface is just a Lorentzian computation. The replica wormhole ones, it's easiest to do as a Euclidean thing and then analytically continue. You can also argue that you can like glue together like Lorentzian patches with forwards in time, backwards in time, but But yeah, morally, that's still doing a Euclidean thing. So really, we should think of that as Euclidean. Yeah. So in when you have Euclidean time going on, then the difference between white holes and black holes is not terribly well defined.
Okay. Any other question or comment? Maybe a very last one from me, if I can.
Yep.
So you said that when you do the computation of the entanglement entropy, you said there are two configurations that you have to take into account. The second one being with one space-time wormhole. Why not two space-time wormholes, 3, 4? Do you have to sum, or they are subdominant, or?
Yeah, for multiple space-time wormholes will generally be subdominant. They'll be suppressed by extra powers of e to the minus the Bekenstein-Hawking entropy, and they won't gain any sort of enhancement, right, relative to the reason the one wormhole one becomes big is that the no wormholes is suppressed by like e to the minus the radiation of the Hawking entropy, the Hawking radiation, and yeah, that can be bigger than the Bekenstein-Hawking entropy, but there's no advantage having multiple ones. What is true is when you have n greater than 2, then sort of long after the page time, this sort of multi-boundary, everything connected in one big space-time wormhole thing dominates. But sort of near the transition, there's also ones where maybe two of them connected together by a wormhole, and then there's a third one off doing its own thing or something. And yeah, these are harder to deal with, but in simple enough time models, you can take their corrections into account, and it doesn't change the qualitative story, but it can give you the details of the exact transition near the page time. So that is something you can understand in very simple time models.
Okay, thank you. I don't see any other question or comment. So let's thank our speaker again. And well, you had to wake up early to talk to us. So thank you very much. This is much appreciated.
Thank you very much for inviting me. No, it was a pleasure to talk. I hope people got something out of it.
Okay, yeah, thank you.
Thanks a lot.
Bye-bye.